first speaker is John Williams. He is the CTO and co-founder of Kudan, and his background is in embedded systems and augmented reality. And today he's going to tell us about Kudan's licensable SLAM algorithm for indoor and outdoor use. John?
Hello, everybody. I hope everybody's refreshed and energetic after lunch. I had to miss most of mine. So a bit of background on Kudan, because we're not quite as well known as most of the companies here. We're computer vision specialists. We mostly focus in SLAM. We've been around since 2011, and in 2018, we went public in Tokyo. It's gone well for us because we currently have a market cap of over $1 billion. So what we fundamentally believe is that SLAM is a technology that should be available for everybody. It enables so many different use cases, which is why I'm on this enabling technologies track. And we do that by making it available as a library. And I'll go into some of the details here. And basically, the theme here is flexibility. So it runs on all kinds of different processors, from your standard general purpose ones like ARM, Intel, but it can utilize all kinds of accelerators as well. GPUs, DSPs, FPGAs, a lot of the details I'll go into later. We're very, very flexible when it comes to sensors. There's nobody that can support as many different classes of sensors in different configurations as us. So, we can do camera-based SLAM, we can work with LIDARs, IMUs, odometries, all sorts of things can be fused together in various ways. Once again, we're flexible in terms of use case. So we've not overly engineered for one thing in particular. So there's some good SLAM systems by, for example, Microsoft for HoloLens, but it's very much built around AR. We've decided to build our SLAM system such that it's relevant to everything. So AR, VR, all kinds of robotics and drones, indoor navigation, 3D mapping, all that sort of stuff. And we achieved that by making it very configurable such that it can be tuned for its use cases. So one of the things that gets really confusing is that everybody refers to anything that has 3D tracking as SLAM. So I think it's marketing directors, SLAM just sounds better, but more often than not, people are making visual odometry systems, and there's quite a dramatic difference. So they have a lot of common functionality. Both a SLAM system and an odometry system will tell you a 3D position, a 6-degree of freedom position. Both of them will provide some data about the environment because that's how they do the tracking. But SLAM does things a little differently. So visual odometry is giving you a position with respect to some previous moment in time. It can be the last frame, it can be 10 frames ago, it can be the frame that was last used in a particular area. But SLAM will make a map, and it will continue to build and improve that map and never throw it away. And this gives you all kinds of advantages over odometry. So there's nice things about SLAM, such that if you are maintaining a map, you don't get any drift when you're in an area that's already been mapped, because you are referencing the map. You're not referencing a previous moment in time. If that map hasn't been updated, it's still going to be the same position in 2 hours, even if you're moving up and down within that area. And the real secret weapon of SLAM is loop closure. So loop closure has the ability to recognize when you are visiting a previously mapped area. And when you can recognize that you've come back to somewhere you've been before, you can actually measure the amount of drift that has existed throughout tracking. And when you've measured it, you can close the loop. So it actually results in far more accurate maps than you could possibly get from an odometry system. One of the nice things is that if you're building a map and you're keeping it for the entire duration of your session, you can always relocalize against it. And that's handy for all kinds of reasons. So an obvious case is if, unfortunately, you lose tracking for some reason, you can pick back up where you left off, and there's no damage done. An odometry system tends to reset when it loses tracking, and that doesn't mean anything because it doesn't know how you've moved in the duration that you lost tracking. So in that time, you could be facing a completely different direction. The odometry system carries on. And what does that do for your use case? Your robot can't navigate. You just don't know where you are. So it doesn't have much, odometry doesn't have a good failure mode. Another nice use case of SLAM is that you are building a map and you are trying to make it as accurate as possible. And a lot of the companies on Showcase today are doing various depth sensors, and that is real-time depth information, so it has its limits. They have a certain range, but SLAM, from its multiple different views, can actually build a consistent map covering much larger ranges than any of those individual sensors can see alone. And that's useful for all kinds of things. So, just an example off the top of my head might be robot navigation. If it's got a whole accurate map to find its way through, that's much better than what you get from an odometry system. If you can relocalize, then you can share maps as well. An odometry system initializes relative to wherever you're starting. So that is the origin. There's no common coordinate system between different devices, which means that user A could map the room starting from this side and user B could start from that side. They have no idea how those two spaces link. If you've got a SLAM system, you've got a map with a common coordinate system, and you can share that with different users. So for example, in augmented reality, you can map this room and place some AR content in a particular area, and everyone that downloads that map and localizes against it will see exactly what you've placed there. So odometry just can't really do that because the map is not its focus. This is a nice example of how SLAM accuracy is just much better than visual odometry. So this is a loop of our office. It's actually 2 loops of our office. So it's about a 100-meter trajectory. You can see that, well, actually, I'll need to tell you, but we start the camera in a very specific position. We walk around the office twice, and you can see in the SLAM case, it's pretty much followed the same line and ended up exactly where we left off. The right-hand side is an odometry system. I can tell you it's Intel's RealSense, but you can see that the trajectory has opened up. So it should be completely closed because we started and ended in the same position, but it's actually drifted vertically. So it thinks you're about 1 meter taller after those 2 loops. So you're trying to use that to navigate a robot, but it becomes meaningless. And this only gets compounded over time. If you were to do 10 loops, the visual odometry system might think you've now gone upstairs, whereas the SLAM, you could do 1,000 loops because it is reusing that map. It's not even changing the map on the second pass or the 100th pass. So 1,000 loops, 1,000,000 loops. I wanted this as a screenshot, but nobody volunteered to do it. So when we look at SLAM, we're evaluating several key properties. So accuracy and processing times are the ones everybody obsesses about. They say, how accurate is it, and how long does it take to process a frame? But accuracy is a complicated thing by itself. There's all kinds of quirks to how you're measuring accuracy. Are you measuring the accuracy of the mapping, or are you measuring the accuracy of tracking against the map? Tracking against the map is much more accurate than when you're mapping. You're always going to have a little bit of drift over large distances with mapping. And loop closure, which, as I said, is SLAM's get-out-of-jail-free card, can hide a lot of error. So you can have some very bad tracking, and loop closure can actually fix the map. But if you don't present it with a loop closing situation, you are now stuck with that non-loop closed trajectory, which could be really bad. And there's quite a few SLAM systems that are very bad until they close a loop. And this is just terrible for robotics navigation. For processing, everybody wants to know the average time, but it's actually more important to know how it varies with length of mapping. Most people test in 2 minutes or something, so there's not much time for change. But if you're going to be using SLAM for an hour a day or something like that, it's very important what its properties are over time and map size as well. And everyone forgets about these KPIs. Robustness is probably the most important one. And this is just not losing tracking when presented with difficult conditions. So there's all sorts of things: motion blur, dynamic lighting conditions, things within the environment moving. And probably another overlooked thing is that if SLAM is struggling, you want it to fail gracefully. You really don't want it to give a best guess and corrupt your map. Because if it can signal to you that it's unhappy, in certain use cases, you can actually do something about it. We have relocalization. You can just move backwards, possibly, to localize against the map and carry on. If it's some industrial use case, like industrial robotics, forklift trucks in a warehouse, if it's unsure, it should just stop. It shouldn't make a best guess where there's safety implications as well. And very few SLAM systems, if any, actually give you much confidence measure of what's happening. Whereas, at least with Kudans, we like to indicate when things are struggling. And other things like memory consumption. We're building a persistent map. You're naturally going to be bounded by memory. And this is going to limit your use cases because, what happens if you use up all your memory in 10 minutes? How far can you possibly travel? And relocalization, it's SLAM, so you've got the luxury of relocalization, but relocalization is much harder than tracking because you have no prior information on how you've been moving. And nobody ever tests relocalization. They assume it tracked so it would relocalize in the same spot. But even worse, when you relocalize, you're not necessarily in the exact same spot you were when you were mapping. You might be, I might have mapped this room from the central area, and I might try and relocalize from that corner. How much invariance is there? Because that is, use case breaking if you have to be on the exact same thing. But nobody ever studies this. And the sad fact is that there's always a balance between robustness and accuracy and speed. You can always trade off speed for improved robustness and accuracy. But it's up to you as a use case, knowing what processes are involved and stuff, to decide what is absolutely most important. But there's no such thing as a perfectly robust, accurate, and ultra-fast SLAM system. You can get close, but there's always compromises if you need it to be fast. So just here's a quick video showing robustness. There's no way to make nice graphs for this, but this is showing different lighting conditions. So this is just standard auto exposure. So not much is happening. You go into a darker room, it exposes a bit differently. Nothing too dramatic. But at this point, we just turn off the auto exposure. So when we come back out into the room, everything's horribly exposed. But it's still able to match against that existing map, such that when you come back, you're exactly where you left off. This is an extreme. It's never going to be this bad in the real world. But if you can handle this, you can handle the real world. This is an example of dynamic environments. So a lot of SLAM tests on videos where nothing is moving. So we thought we would do something that actually involved everything moving. And it's a little tricky to see in the right-hand view of the map. But every time something gets added or moved, it actually updates within the map, which is why points are flicking in and out. So the map can actually evolve over time. So as long as you continue to move through an environment, it will update to the latest status of that environment. Accuracy is always a tough one to present. So we measure accuracy by doing ground truth. So that's done from motion capture or something like that. So this is roughly a 100-meter trajectory from a drone and measured with a Vicon system. And we get roughly 20 millimeters of error across the whole 100-meter trajectory. So it might be a bit hard to see on the projector, but green is the ground truth, blue is our estimated trajectory, and the little pixel width of red is the error between them. So for large parts of the trajectory, it's actually almost perfect. Processing time. Now, this is why I said the mean doesn't matter. So this high spiky looking thing is actually OrbSLAM, which is probably the most popular academic SLAM system to date. Now, if you were to calculate the mean for that, you would actually think it's not too bad. But you can see two things going on here. Is that one, over the duration, which is the x-axis, it actually starts to slow down. So it's about, 20% slower just about 3 or 4 minutes into the video. And this will actually continue. But the very worst thing is these horrible spikes. Because when something is moving, a robot or something like that, you get a spike and you don't process camera data for the duration of that spike. And some of these spikes go up to 250 milliseconds. Now, what can your robot or autonomous car do in 250 milliseconds? Quite a lot, and you don't want to miss it. So the green and the red is Kudan, and you can see we actually are pretty constant with regard to time and map size. So the processing time doesn't increase as we grow the map. We're also much less spiky, so there's a lower standard deviation. And we have two modes, and the red mode is actually our fast mode, where some settings have been chosen to speed things up. Memory is an interesting one as well. OrbSLAM just seems to just go crazy with memory. So this is an interesting sequence in that halfway through, we start going back into the existing explored environment. And I'll show you another graph in a second, but what actually happens is we reuse the map, so we don't gain any memory, but SLAM does all sorts of horrible stuff. So it uses more memory in general, but if you look closely at us, once we get the halfway point, so this is zoomed in now, we actually reuse the existing map and memory size stays constant. So memory doesn't grow with time, it grows with expanding into new areas. So one of the main things Kudan does is support lots and lots of sensors. So there's all sorts of sensors you can use for SLAM. They have various pros and cons. Cameras is the obvious one. Monocular cameras is quite a nice use case because it allows you to use cameras that were not intended for SLAM. This is typically what happens on mobile phones. But SLAM, from a monocular point of view, does struggle, and you really do want a source of real-time depth. And that source of real-time depth can come from all sorts of things. So it can come from stereo systems, any kind of RGB-D camera, time of flight, structured light, all the sorts of things. It can even come from LIDARs projected into the camera and stuff like that. So here's an example of a time of flight RGB-D camera we built, although it's not too RGB-D. It's grayscale, but you get a nice dense map, and that's useful in augmented reality for occlusion reasons. LIDAR is the big daddy of sensors. It's the best thing you can have outdoors because it has such high range. It also presents a 360-degree view. So it's just very, very good outdoors, and it can also see in the dark, so it just doesn't care whether it's day or night. And this is the reason all autonomous car companies use LiDARs and have several LiDARs, unless you're Tesla and you think it makes the car look ugly. So this is an example of a LiDAR map. You can see it is able to map in all directions from just one pass because of the full 360-degree views. IMUs provide very high update rates, which is nice for AR because typically cameras are too slow. You want to reduce motion sickness. And GPS is just something that if it exists, it's worth using because it's very good with global accuracy. It's locally inaccurate, but it's very accurate globally. So why do you want to combine sensors? The real reason is that there is no perfect sensor. And even just moving through a certain environment, whatever the most successful sensor is can actually change several times. So lighting conditions like I showed you, but also cameras start to struggle with very bare areas, whereas IMUs and LiDARs don't. But you don't want to just fall back to one sensor. You want to actually utilize all the sensors you have all the time. So there's actually nice things you can do, like project LiDAR points into a camera and make it like a mega range stereo camera effectively that can see for hundreds of meters. And you can deal with all the bad stuff about IMUs by fusing them tightly with other systems like cameras. And IMUs by themselves are terrible. So our approach to sensors is we support pretty much everything. If you come to talk to me afterwards, you'll probably find like some niche case that we haven't. But in general, we can support all sensors and all combinations. So single camera, multi-camera, camera plus IMU, camera plus IMU plus LiDAR, LiDAR alone, LiDAR plus IMU, all those sorts of things. Pretty much the only ones we don't do is pure IMU because it's just not very good, and pure GPS because that's just GPS. We don't care about sensor details, so model of camera, type of LiDAR, like number of scan lines, just doesn't matter. And we can toggle all of them off dynamically, so you don't need for a given frame data from all these different sensors. And calibration is kind of a big thing, but we can, it gets complicated once you have multi-sensors, so we have various things in our SLAM to help with that. Common setups, fisheyes plus IMUs are usually good for stuff. They have large field of view, and IMUs help with robustness. You can start dealing with better sources of real-time depth for more sophisticated use cases. And cars, generally, you add everything you possibly can. They don't have any power limitations or anything like that, so you can just throw everything in for the maximum performance. And in the future, a new class of camera called event cameras. There's some representatives around in the showcase over there, but they're going to enable quite a few interesting things with SLAM. Let's talk about processors. So this is another thing where we're really flexible, but we want to kind of highlight the benefits of this. If you have a higher frame rate and a lower latency means you get the data more quickly, so you can act on it. In AR cases, this means much less motion sickness. In robotics cases, it means it's less likely to crash because it's not got that delay before it knows where it is. Faster makes things more robust and more accurate because you're able to process more frames. And if you just make things efficient, you can reduce power consumption, which lets you SLAM for longer. And like you saw with the memory usage stuff, if you're frugal with memory consumption, you can expand into large areas. How we make things fast, everything we do is optimization is probably the most important thing. So for our general purpose processors, it's all heavily optimized using the SIMD instruction sets. Everything's very multi-threaded, so if you want to throw more cores at the problem, it should scale fairly linearly. But probably the biggest thing we do is we support all these different classes of accelerator. So GPUs via OpenCL and CUDA, but also DSPs. We've got a partnership with Synopsys at the moment and also FPGAs. We can even do processing on the cloud to lighten the load on the actual devices. And unintuitively, sensor fusion can actually make things faster because you have a much better expectation of where to look for things, so you don't have to process as much. So if you really want to port to your processor, we've made this very, very easy. SLAM, the heavy things within SLAM are basically image processing, pose estimation and bundle adjustment, which is nonlinear optimization, and dealing with map data. And we've chosen to focus on the image processing because that's the thing accelerators are really good at. They're not good at working with map data. They're not great with floating point and stuff like that. But everything is weighted towards that. So if you can get it accelerated, you get huge speed ups. And deep down, everything we've built, we've used building blocks that are commonly available. So these are things that are available in OpenCV, which means if you have a library for your particular chip that's already got optimized versions of things, we can just drop it in and benefit right there. Nothing has to be custom made. And if you do nonlinear optimization, it's not recommended, but we can do single precision floating point, which is obviously really important on DSPs and anything like that. How we cut back on power consumption is interesting. Normally you would just make things very efficiently implemented, but we have some functionality that helps with that. So because it's SLAM, when you explore a map, when you return to a new area, the map doesn't have anything to do, and that's the heaviest part of SLAM. When you share maps, you completely remove that again. Why, every time you move in the same room, why should you be mapping constantly? And we have different types of power saving mode as well. So we can switch to lighter forms of tracking when we detect that not a lot is going on. And this can dynamically save a lot of power. And we can propagate this to your sensors as well. So we can actually control when sensors get turned off based on whether SLAM needs them or not. So you can turn off a LIDAR, which is quite high wattage, and benefit massively from that. Memory usage, you are going to run out of memory in SLAM as long as you're maintaining a map. But we have all sorts of tricks to cut back on that. So we get rid of redundant map data, so we only keep what's absolutely necessary. But we can also stream map data to and from other forms of storage, disk, network. So that allows you to map indefinitely, and that's what we do with autonomous vehicles. And we have other modes that are kind of like a hybrid between SLAM and Odometry, and they will eventually delete stuff when you finally reach a limit, but it has much more benefits. This is an example of a map we've made over about 10 kilometers of driving. It's got 1 billion points in it, and it involves streaming to and from disk, which is the reason we were able to do it, because 1 billion points would otherwise be several gigabytes of RAM. Why commercial SLAM? So I'm just going to address why not academic SLAM, first of all, which is that there's too much focus on one particular thing. And for SLAM to be effective, it doesn't need to be that creative. It just needs to be done well. And essentially, these things are very tricky to optimize because they are not, they're not designed to be. So the thing I said about, a large percentage of us being image processing, so it's friendly for accelerators, is not the case with academic SLAM systems. And just general lack of quality. If you've looked at the code, you know. And there's no points for them supporting lots of different stuff because deep down, they're getting a PhD for doing something novel, not for supporting a wide range of things. So why do you want to work with Kudan? So we focus on SLAM. It's what we do, and we've done it for a long time. And SLAM is not as easy as reading some papers and implementing it. You actually have to try and fail dozens, even maybe hundreds of times before you settle on what works. And we've failed on all sorts of stuff and arrived at a refined solution. We've covered every industry. You're not going to be able to tell us about one that we haven't already worked in. So autonomous cars, robotics, AR, VR, we know what works in all of those sorts of things. But most importantly, you can use your existing hardware. You don't have to redesign your hardware to use a particular SLAM system, which is just something that's, a lot of solutions require that, and it just adds so much cost. And we can add custom functionality. We can just do various things that are necessary for you, so you don't need to do an in-house one to achieve that. So I've timed this perfectly. But essentially, if you want to work with us, we license out the software, but we can work with you. We're very flexible in terms of working. If you make a processor, we can help you port to it. If you make sensors, we can help integrate or optimize it. And if you're actually developing something that uses SLAM, we will help consult with it and actually arrive at the best solution. So if you want more details, come and visit our website. But we have a booth over there, and we're here for the 2 days. We're in the Bay Area all week. So if anyone wants to come and talk to us, we're here. And thank you for your time. Thanks.
So I'll start with the first question, which is, I'm curious, how many, ballpark, how many licensees, how many designs, can you give us some idea?
We've worked with hundreds of customers over the years, from deep level tech, processor companies, all the way up to solutions.
Hi, thanks for the presentation.
Thanks.
It was very informative. This example that you gave with the 100-meter loop
Yep.
and 20 millimeters error, I guess it's cumulative error. What sensor did you use, and how do you measure ground truth?
That was in the one where I showed the trajectory.
Yes.
So that was just, hello? Oh, just a stereo camera. And we measure it because there is a Vicon system and a LIDAR laser tracker that provides the ground truth. So the ground truth is much more accurate than what any SLAM system can actually achieve. You're sub-millimeter.
Okay, so I guess LIDAR is used as the golden standard in that case, right?
Yeah.
Okay, thank you.
Hi, thanks for the interesting talk. I'm sorry I missed the first part of your presentation, but I'm here now. Some self-driving car companies are separating the localization and the mapping. They do mapping first and they do localization later, whereas SLAM is simultaneous. It does both of them together. So I just wanted your thoughts on why SLAM versus mapping and localization separately, and how your offering might coexist or compete with this technology and advanced industry in general.
So essentially, we want the map to be a kind of a product of the system. And one of the benefits of continuing to do SLAM is you can pre-map an area and just share it. But deep down, these areas do change. And it's nice if the devices that are localizing against them can actually update the map. It saves you from having to send out a mapping car every 2 weeks or something to cover every possible area, when you can essentially crowdsource it because SLAM is continuing to run and feed it back in that way.
Hello.
Hi.
Thanks for your talk. I have a question about loop closure. Are there ways to correct drift other than loop closure? Because I'm afraid sometimes in real-world cases, there might not be loops. And before you get to a loop, maybe the trajectory you outputted already has a drift.
Yes.
Yeah.
So essentially, you can use other sensors. So GPS is very good at correcting large-scale drift if you fuse it in. So GPS is accurate to about 4 meters, which is terrible if you want to localize like that. But if you want to travel 10 kilometers, it's suddenly very good. So you can actually correct things without a loop by using the right type of sensor. Or you can manually correct loops through annotation as well. If you're, like the previous question, if you're making a map first, it's something that you can correct manually.
Thank you.
Thank you. Thanks very much.